Okay, now we've seen that if we map this vector by the transformation given here, we get this vector, and if we want to get this vector, we figured out that this is the vector that we would have to map. Now, if all these calculations are done right, everything should work out nicely. If we add these two vectors, we're going to get what? We're going to get the vector 7, negative 1. Okay, so this V and this V, and I should be using the same notation for both V's, shouldn't be using a notation W for both W's. So, really what I want to do is subscript this V1 and V2, but then it gets confused with the components of V1 and V2. So I'm going to call this V hat, and I'm going to call this W hat, just to distinguish the two V's and the two W's. In any case, now, if I add V and V hat here, I get the vector 7, negative 1, which will be out about here. And I wanted to use a different color. I grabbed the wrong piece of chalk. Okay, so if I, do parallelogram or whatever, I get the vector V plus V hat equals 7, negative 1. If I add these two vectors, well, again, I can do parallelogram just to see where that's going to be. And it's going to go right through a lot of my labeling, but we know what I've already said, so. Okay. We get this vector, which is our W plus W hat. Not a lot of room to label it, but I'll do my best. W plus W hat equals, well, 15, 6. Okay, now my question is, if I now transform 7, negative 1, do I get the vector 15, 6? Okay, now, if the transformation is linear, then this should be the case. Because definition of a linear transformation, which we haven't given, is that if you transform the sum of two vectors, you get the sum of the two transformed vectors. Okay, so if I transform V to get W and V hat to get W hat, then if I transform V plus V hat, the vector I get is W plus W hat. Now it might seem obvious that that ought to be the case. Well, that is the desirable case, but it's not always so. There are plenty of transformations I can define that don't do that. However, any transformation where this is a linear combination of V1 and V2 and this is a linear combination of V1 and V2 will have that property. Now let's just work it out for these vectors. Now I need to, well, maybe I can remember. Okay. So I've already written a couple of statements. I'm saying that this transformation is linear. I know in advance that if this is a linear combination of V1 and V2 and this is a linear combination of V1 and V2, it will be linear. So I know this transformation is going to be linear, but I haven't proved any of that. I haven't even defined linearity. Okay? Now, there's a little bit more to the meaning of linearity than what I've written down here, but this is kind of the essence of it. That T of your V vector, which I'll call T of V1, V2, and plus T of U1, U2. Now, maybe my notation's getting a little bit confused. Instead of V1 hat, V2 hat, I've used U1, U2. But that's the general way we define it. We don't want to start putting hats and things. If you get too many of them, how many hats can you put on a vector, or how many tildes, or whatever. So I'm going to use u1, u2, and v1, v2 for the two vectors that we start with. Now, v1, v2 on our picture, if you recall, v1 and v2 were 3, negative 4. And then our vector I called v hat, if its components are u1 and u2, that one was 4, 3. So again, if I transform 3, negative 4, we know that I get 10, negative 1. If I transform 4, 3, we know that I get 5, 7. If I then transform this vector plus this vector, which would be 3 and 4, which is 7, 4, negative 4 and 3, which is 1. Okay, and we saw that. We have these two vectors, they add up to 7, negative 1. If I transform 7, negative 1, do I then get the vector, what was it, 15, 6? Yeah, I get the vector 15, 6. Well, let's see how those things work out. I know what v1 and v2 were. I know what w1, which is a transform of v1, v2, and w2, which is a transform of u1, u2 equal 4, 3. Were 10, 1, and 5, negative 7. So, my transformation of v1, v2 is 10, negative 1. My transformation of what I'm calling now u1, u2 is 5, 7. Okay, now, see 10, negative 1 and 5, 7, just to make sure we see it. Right there's our 10, negative 1 that we got from this one, our 5, 7 that we got from this one. Is that equal to what I get if I transform v1, v2 plus u1, u2, which is v1 plus u1, v2 plus u2. And I'm going to write that out. This would be the transformation of this vector plus this vector, which is 3 plus 4, negative 4 plus 3. Okay, so here and here are these components, which are these and these. So you can think through how this expression gives you this. And of course then that would be t of r7, negative 1. And remember 7, negative 1 was here. So we're seeing if transforming this 7, negative 1 will give us our 15, 6. Well, if we transform 7, negative 1, we get 2v1 minus v2. 2 times 7, I guess I'd better write it out. 2 times 7 minus negative 1, and 7 plus negative 1. Well, lo and behold, that equals 14 minus 1 gives us 15, and 7 and negative 1 gives us 6. Well, what were we checking? We checked if we transform this vector, do we get this vector? This vector being the sum of these two, we transform it, do we get the sum of the two transformed vectors? Well, the sum of these vectors is easily seen to be 15, 6, and that's exactly what we wanted. Okay. And I probably should have noted that T of V1, V2 equals this, T of U1, U2 equals this. Okay, if I add these two vectors, I get this. And now, if I transform the sum of these two vectors, that's exactly what I get. Okay. Now, linearity means the T of V plus U equals T of V plus T of U. Make sure you understand what that's telling us in terms of the example. Also, T of some multiple of V is equal to that multiple of T of V. Now that kind of follows from this, but we generally list it as a separate criterion for transformations. If a transformation is linear, it can be represented by a matrix in a way that I've already pretty much demonstrated. Now there's much more to this, but that's sort of the essence of the connection between linear transformations and matrices. And of course, if it can be represented by a matrix, then you can define a linear transformation just by a matrix. Okay. Representation and the linear transformation itself are, in a sense, identical or isomorphic, or they can be identified with one another. Doesn't matter which way you represent the thing.